How does a weakening in AMOC influence the climate of New Zealand? Well, the weakening or collapse of AMOC has disrupted New Zealand's climate in the past, and it could very likely do so again. Hello friends, Jim here. So what's going on? Recent assessments suggest the ocean current, AMOC, right, is slowing down, with collapse a real possibility this century. It's slowing down. It's hard to say whether it will collapse. I'll reserve judgment on that. AMOC is a globally important current in the Atlantic Ocean, where surface water moves northward, part of the Gulf Stream, and it continues as the North Atlantic Drift. It transports warm water towards the Arctic. It cools and sinks to return southward as a deep ocean current, but brings some cooler conditions to the lower latitudes. Collapse of AMOC would have a devastating effect on the climate in Europe. Temperatures in UK and Scandinavia could drop by 5 to 15 C in a matter of decades. However, Earth's climate system is interconnected, so these impacts could have a global reach. Our new research, that would be these folks here, Sean Eves, Andrew McIntosh, Helen Bostock, and Joel Pedro, shows past changes in AMOC have had a significant impact on temperatures in New Zealand and across the southern hemisphere. These results imply the future collapse of AMOC may accelerate ongoing warming trends. Wow. Well, they're talking about the southern hemisphere. Evidence indicates that as the northern hemisphere cools down, the southern hemisphere warms up. But if AMOC slows down, the southern hemisphere may start warming up. Between 20,000 and 10,000 years ago, Earth transitioned from peak ice age conditions to a climate like today. This interval featured rising global temperatures, melting ice sheets, climbing sea levels, which are related or associated with present-day conditions. Evidence from ice cores in Greenland and marine sediments in the North Atlantic suggests this natural warming event featured several abrupt changes associated with AMOC variability. Using this interval as a natural experiment, we've undertaken research to learn how AMOC variability impacts New Zealand's climate. So they, what was the air temperature like? So they looked at the past extent of mountain glaciers, looking at the evidence in preserving the landscape. Glaciers grow and shrink primarily in response to changing air temperatures, which affects the annual balance of snowfall and snow as ice melt. Glaciers change in size, they deposit more rain, rocks, in the landscape, which can persist for a long time. So they combine those land-based observations or proxy data with reconstructions of sea surface temperature in the Tasman Sea, which they derive from microfossils, smaller than 1 millimeter in size, known as forams, foraminifera. And they probably also looked at the oxygen 18, oxygen 16 ratios, possibly even nitrogen 15, nitrogen 14, as well as carbon 13, carbon 12 ratios. These are typical isotopic ratio fractionation that are used to reconstruct past climate, past environmental conditions. We quantified changes in foram species in the core of marine sediments to trace how local temperature in the Tasman Sea vary through time. Different foram species have different temperature preferences. So if by looking at the species makeup, you can ascertain what the temperature conditions most likely were. Our results show that changes in air and sea surface temperature followed a similar pattern in the New Zealand region as Earth warmed following the last ice age. Warming began in both air and sea about 18,000 years ago, followed by a cooling event about 14,500 years ago, known as the Antarctic Cold Reversal. The timing of these changes matches past changes in AMOC as recorded in geological climate records from the North Atlantic region. We then looked at computer simulations to test the physical connection between changes in AMOC and New Zealand's climate. Those simulations used a physics-based climate model that looked at atmospheric ocean circulation and their interaction. That's important, the interaction. The model simulations support our geological evidence showing air and sea surface temperatures in New Zealand respond sensitively to changes in AMOC intensity. When the AMOC weakens and Europe cools, New Zealand and the southern mid-latitudes undergo warming and vice versa. Models also indicate changes in AMOC are transported rapidly within decades to New Zealand via shifting global wind systems. Changes in AMOC disrupt the temperature gradient between the hemispheres, which is a key control for the strength of westerly wind belts in the southern hemisphere between the latitudes of 40 degrees south and 60 degrees south, where New Zealand is. The westerly winds are important for New Zealand's climate. They control the path of atmospheric storms and regional ocean currents. Stronger winds over New Zealand bring regional cooling as more storms track over the country and warm ocean currents are diverted away from the Tasman Sea into the South Pacific. In contrast, when AMOC weakens, New Zealand has clearer skies. Tasman Sea receives more tropical water masses, causing regional warming. It's because, well, that's right, you have ocean heat content diffusing to the atmosphere. So, there's some future implications, of course. Scientists have identified several tipping points in Earth's climate system that may be triggered by human-caused climate change. Once these thresholds are crossed, the consequences cannot be easily undone. In other words, you can't unring the bell once it's rung. Climbing greenhouse gas concentrations have raised air temperatures in New Zealand and globally by about 1.1 cc since the late 19th century. It's higher, much higher, like 1.5, 1.6 globally. Projections suggest New Zealand may end the century 1 to 3 C warmer than now. Models show at least a 5 C warming for the planet, probably 7 to 11 C by 2100. However, these estimates do not include the potential impacts of a future AMOC collapse. So let's take a look at this figure here. Okay, so basically a description. That's the big boy up here, the panel up here. Location of our marine and terrestrial study sites within the context of regional oceanic and atmospheric circulation in the Southwest Pacific and Southern Oceans. So B shows the relative positions. Okay, you see a dashed square here and a yellow dot here. Okay, there's your yellow dot. And within this dashed square is a red square, which is right here. So the yellow dot is an oceanic study, and the red square, or the red dot here, is up in the mountains. So, oops, didn't want to do that. Come on. So what do we have here? You can see Australia here, right? Here's New Zealand, right? You have the East Australian Current. The Lewin Current. Here's the extension of the East Australian Current, the Tasman Sea. So here's New Zealand, of course. And You have a subtropical front here. You have a subantarctic front here. Then we have the polar front. And we start getting down to Antarctica. So here are your latitudes. 20, 30, 40, 50, 60, 70, 80, right? And here are your sea surface temperatures. So this is the coldest temperatures as you would expect. And you can see how it gets really warm here. Right? We're talking in the 20 to 25 vicinity. This is in degrees C. Over here, we have the wind speed in meters per second. And as you can see, it is highest in the 40 to 60 degree belt, or about 50 degrees, which puts us in the subantarctic front. So when AMOC is running strong, you have strong winds here, it pushes the warm water out away from New Zealand. It brings in some storm activity, and you get cooler conditions. When AMOC slows down, the winds slow down, and then you get the accumulation of the warm waters warming things up. That's basically what they're saying here. So this is interesting. Again, this shows how everything is connected. Atmosphere, ocean, it's a coupled system. And what may seem to, people think, oh, what goes on here has no impact, far away, is incorrect. Everything is connected. All the oceans are one big oceans. Something happens with the ENSO cycle, impacts, the NAO, impacts hurricanes. You have the movement of the Aleutian low, which is in conjunction with, again, ENSO pattern, affecting what goes on in Siberia and Alaska and the Yukon and Nunavut territories, right? And so on. Well, what happens with the Pacific Decadal Oscillation, ENSO, impacts the Indian Ocean dipole. Everything is connected. So something takes place in the North Atlantic, you feel it all the way over in the South Pacific. Interesting. Until we talk next time, thank you for your time.